All right. So the gradient is always orthogonal to the contours, right? Because moving along the contours, you're not changing the objective function, right? You're not changing the function. So the gradient direction always the direction that points orthogonal to the contour. Now imagine I didn't draw the contours to be fine enough, but like if I draw the contours to be a little bit finer, let's actually get to a particular contour of the red on which there is a tangency happens. There is always such a contour line, right, where the objective function has that contour tangent to the constraint. So on that point, what's special about that point? The thing special about this point is if you keep on the blue line, either moving up or moving down, you are getting out of that contour, right? Going up or going down, you are both increasing the objective function. There is no direction you can move to further decrease the objective function. Isn't that the definition of optimum? While for any other point, again, if you focus on a green point, like over here, just to exaggerate, and you draw the contour of the red that passes along here, it's not tangent while they actually intersect. So what's the problem about intersecting? If you intersect, then there is always a direction on the blue line you can go to get inside of that contour, right? As long as you get inside, you are decreasing the objective function. So you're no longer, you're not at the point where your objective function is minimum, even taking into consideration that I'm constrained on the blue line. So the answer is that basically the constraint minimum is at a point where the contours has to be tangential to each other, and because the contours are always orthogonal to the gradients, the contours being tangential means the gradients are pointing towards the same direction. All right, the gradients of J is pointing towards the same direction as the gradient of CE. Okay, so now what's the value of lambda E then?
-1.
Huh?
-1.
No. So if you take the gradient of J versus CE, they point towards the same direction. They point towards maybe the same, maybe the opposite direction, but like they're not of the same magnitude. And lambda E has to be whatever it is to kind of make the magnitudes to be also the same, right? Only if that's the case, the whole thing would have a gradient equal to 0 at the same optimal point, right? Huh? Okay, so to conclude, my partial J, partial S, plus whatever the value of lambda E has to be, times the partial CE, partial S, has to be exactly 0. This is the statement that says that the two gradients has to point towards, has to be aligned, right? Or the two contours has to be tangent. All right. Okay. And another thing is that this equation has how many variables and how many equations? If you look at this equation, if you assume you know the form of J and CE and you want to solve it, how many equations does it have, and how many unknowns do we have in this equation?
If S has n variables and n equations, n plus 1.
We have n plus 1 unknowns, but only n equations, right? Because we have n unknowns being all the components of S plus the lambda E that we don't know. But here, the derivatives are with respect to all these n components, so we only have n equations. Where's the remaining equation?
That lambda E has to be the magnitude of the gradient of J divided by the magnitude of the gradient of C.
But that's already implicit in that equation.
C
CE equal to 0, exactly. The constraint itself, right? So this basically completes what we need to do to formulate the so this is called the first order optimality condition for constraint optimization problem. Some people actually write the C equal to 0 in a more maybe you can call it elegant way. This is basically saying that if you look at this whole thing, CE is the derivative of this whole thing with respect to lambda E, right? So some people just define this whole thing being a Lagrangian. So the Lagrangian is a function of S and the lambda E. So that's defined as J of S, right, plus lambda E times CE of S. And then these two equations can be written such that partial L partial S is equal to 0. That's the first equation. Partial L partial lambda E is equal to 0. That's the second equation, right? So basically, if you just define another thing called the Lagrangian, the optimization problem I have originally is converted into an optimization problem of one more dimension, but the constraint is now gone. So that's kind of the Lagrangian multiplier method of solving this optimization problem.